Hi, I'm Andrea, and this is AP Physics C Mechanic FRQs. Today we're going to talk about 2019's Set 1, Question 1. The question says, in an experiment, the student used video analysis to track the motion of object falling vertically through a fluid in a glass cylinder. The object of mass, 12 grams, is released from rest at the top of the column fluid, as shown above. The data for the speed v of falling object as a function of time t are graphed in the grid below. A dashed curve represents the best fit chosen by the students for data. Okay, so overall, at first glance, it's an object being dropped in a fluid. So the question would probably have to deal with a drag force from the fluid. So we should keep that in mind. And they give important information of object M, which is mass. I like to convert it right away to kilograms. So it's going to be 0.12 kg. Hi, this is Andrea editing from the future. I made a mistake. The mass is not 0.12 kilograms. It's actually 0.012 kilograms. So whenever you see m equals 0.12, you should know that it's actually 0.012. With my mistake, you should take away that it's very important to get your conversions correct, because otherwise the answers you have for each section of the question will be wrong just because you forgot that 0 or misplaced that decimal point. Alright, back to the question. And another important information is the object is released from rest. So its initial velocity is 0 meters per second. Yeah, and then they give the graph of velocity over time. So probably is going to be something also with the relationships of displacement, velocity, and acceleration. So that's the overall view. Going into question A, let's first go to I. Does the speed of the object increase, decrease, or remain the same? So this one, you just directly look at the graph because they give you velocity over time. So as time goes on, the velocity does increase. No justification needed because the question didn't ask. Part A, double I. In a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. So we know that the object experiences both a gravitational force and a drag force, and we know that the object is released at rest. So since the object is falling towards the table, it should experience an overall downward acceleration. If it didn't experience any acceleration, it would just stay at rest. If it were to experience an upward acceleration, it would be flying up into the air, which that does not happen. So we know that the direction of the acceleration is downwards. So for how the magnitude of the acceleration changes as the object falls, we can use the displacement, velocity, and acceleration relationships to find the acceleration over time graph, because we have velocity over time graph. The acceleration over time graph is the derivative of the velocity over time graph. So we just basically see how the slope changes from the velocity over time graph. So we can see that at the start, there's a noticeable amount of acceleration, but as the time goes on, we have a noticeable decrease in the slope. So the overall magnitude of the acceleration decreases. But in these questions, you have to write in sentence format because it asks for a brief statement. So on the real test, I would write, the direction of the object's acceleration is downwards, and the magnitude of this acceleration decreases as the object falls. So for A part 3, it says, using the graph, calculate an approximate value for the magnitude of acceleration of the object at t equals 0.2 seconds. This question asks about the relationship between velocity and acceleration again. So if we want to find the acceleration of the object at t equals 0.2, we find the slope of the graph at t equals 0.2. So this line is very thick, but on the real test, you're going to have a pencil, which is much thinner, and definitely use a ruler. Use this line and find 2 points to approximate the value of the acceleration. Just find the slope of this line, and make sure to approximate it to at least 3 significant digits. Your answer for the acceleration should come up to about 2.22 meters per second squared. Don't worry if it's a little bit more, a little bit less, because this is all approximation and everyone draws the line of best fit slightly differently, so everyone's gonna get a little bit different values, but as long as you're within a reasonable range, it will be okay. So let's move on to part B. The students use this equation to model the speed of the falling object to find the best fit. Coefficients are a equals this and b equals that. B used the above equation to derive an expression for the magnitude of the vertical displacement yt of the falling object as a function of time. One key point of this is derive an expression. This question explicitly says to use the above equation to derive. So you must use the above equation to start your process. The second point is that it's asking for the yt graph, and we have the v of t graph, so we can use the displacement, velocity, and acceleration relationships to find y of t. So important thing to remember is that the displacement graph is the integral of the velocity graph, but we need a specific point to help us find the actual equation. At time equals 0, the displacement is 0. So I like to use the 0.00 to help me figure out what the heck this graph is. So now it's time to basically use calculus. So v equals a of 1 minus e to the negative bt power. V, you can change that to dx dt. And then right side you can keep the same, and then move the dt to the right side, so you get dx equals a 1 minus e to the negative bt dt, and then you integrate both sides. And the most important thing is the limits of integration, so you gotta get those right. So for x, it's basically 0 y of t, and this one it would be 0 to t. So we know that the left side will become 2y of t. And for the right side, we can take the a out, so then it becomes integral of 0 to t, 1 minus e to the negative bt dt equals a of t minus negative 1 over b e to the negative bt, limits of 0 and t, which equals to a of t plus 1 over b e to the negative bt. And so then when t equals 0, so it's minus 1 over b. This is a bit cramped, but when you have the actual test, you'll get more paper to write things out clearly and all on one line. So now I have the equation for the y over t. B2 says derive an expression for magnitude of the net force exerted on the object as it falls through the fluid as a function of time. This question is talking about force of time. So to find f of t, we need to find first a of t, which is a derivative of the velocity graph. So since we're finding the derivative of the velocity graph, we don't have to have an actual point to start with. So I just like to go if t equals d dt, a 1 minus e to negative bt. And based on calculus, you should know that you can take the a out. It becomes a derivative of 1 minus e to the negative bt. But we know that that becomes negative b e to the negative bt. So double negative cancels out and becomes a times b times e to the negative bt power. But what we're looking for actually is the force over time graph. So we know it equals to mass times acceleration. So we just multiply the mass of the object to the acceleration over time graph. So our final equation should look like m times a times positive b times e to negative b t power. And of course, because we actually have the numbers for the coefficients, you should plug them into the equation to get actual numerical values, because I know I tend to make small mistakes when multiplying a lot of coefficients together, so I'd rather keep the variables there. But on the real test, I recommend plugging in the coefficients. Alrighty, part C. Students repeat the experiment with a taller glass cylinder. It's filled with the same fluid. The cylinder is tall enough so the object reaches a constant speed, terminal velocity, which is important because that means there's no net acceleration, which means Newton's law of F net equals ma is really important and probably will be used in the next few questions. So for C, part I, determine the constant speed of the object and justify your answer. So I initially thought that maybe we can use Newton's law, but Newton's law doesn't really give you a definitive velocity out of F net equals ma equals 0. So when your initial plan doesn't work, you should always go back and see, oh, like past parts equation might help me with this problem. So if you look back at part B, we're given the velocity equation over time. Since we know that the object is reaching terminal velocity, the velocity should be approaching a certain value. So we can use this equation and find out what actual value v is approaching. Since we're looking for the value that v is approaching to, I like to use limits. So back to calculus, limit when t approaches infinity. you don't have to show this process because a lot of people can already see that v will approach a when t approaches infinity. So we have to state that v equals a, and we have to justify our answer. So you can justify your answer by saying, oh, to find the constant speed of the object, you need to set time equals infinity and see the value that v of t approaches. That would be my justification. So for question C, part I, determine the force exerted by the fluid on the object at this time. We've already said that time will approximate infinity. Keep this in mind. But we also know at this point that the object is at a constant speed, so there's no net acceleration. So I immediately think of Newton's second law, force equals m times a, which equals 0. But we should look deeper into the components of the net force. So we have obviously force due to gravity, but we also have a drag force from the fluid, or as the question says, the force exerted by the fluid on the object. So the force of gravity is going downward, but the force exerted by the fluid is going upwards, going against gravity. Since they're in opposite directions, the gravitational force minus the force due to fluid, and this will equal 0. So we know that the gravitational force is equal to the force exerted by the fluid. And good thing for us, we know how to calculate the gravitational force, which is just mg. We have the value for m. You know the value for g is 9.81 or 9.8 or 10. I like to use 9.8, so you just plug in numbers and get 0.1176 newtons. So it's about 0.12 newtons if you use g equals 10, but that's your answer. And for justification, you should write a sentence. Technically, equations could be counted as justifications, but it's better to give explicit sentence justifications. So I'd write the object is falling at constant speed, which means it has no net acceleration, which means it has no net force. And so then the gravitational force must equal the force exerted by the fluid, because those are the only two forces acting on the object. So then the force exerted by the fluid equals this number. And you completed question 1. So if you're still kind of confused about how in the world did I understand, oh, there's going to be, I need to use Newton's forces, or oh, this question needs to use displacement, velocity, acceleration relationships. So there's a link in the description that will lead you to a list of my categorization of each FRQ problem overall, and each component of each FRQ problem over the past decade, their categorizations, and each big concept will have a link to an explanation of how to identify a problem needing this concept. I hope that this question makes sense to you now, and see you in the next explanation video. Bye bye!